In this recording, we're going to explore vertical dilations of functions, specifically quadratics. Vertical dilations of functions are something we haven't talked about yet this year, so these are a little more challenging. As noted here, if you have a k value, a number that's not 1, it's going to stretch the function as long as k is greater than 1. It's going to compress or shrink the function if k is between 0 and 1. We already talked about what happens if k is negative, and obviously if k is 0, it just kind of wipes out the function. But we've seen this effect, right? Go back to our gizmo here. If I change the value of a, all right, if I change the value of a to be something greater than 1, it makes the graph stretched out vertically. Okay, it kind of looks like it gets narrow, but stretches it vertically. And if I make the a value, the number in front of the function, I know it's kind of a little confusing there because it's in a different format, but this is vertex form, this is polynomial form. But if you look down at the bottom, the a value is between 0 and 1, and it's making the parabola compressed or wider. It's pressing it down in the y direction. All right. So hope that wasn't confusing to you because we used k here as the constant. That's just what they used on this particular document. But the number in front of the function, the stretch, here is k. All right. So cool. It says determine functions for both g and h. How about we do g together and you can figure out h on your own. So if I want to do 2 times f of x, I pretty much need to double all of the terms' values. So g of x, that'll just be mental math. That'll be 2 times x squared minus 8x minus 5. So go ahead and work out on your own h of x and play the recording. And so h of x, simply you're going to multiply by half, which is like dividing all of the coefficients or parameters by 2. All right, so we have h and g, and now let's consider what those graphs might like. And what we're going to do here is just simply use the calculator to explore that a little bit. You already had an inkling because of the sort of the formulas up at the top, but I'd rather you experience that for yourself. So let's grab our calculator if you have one, and let's make each of these graphs. Now, before we go on, I did catch a little mistake. Hopefully you notice that there's a little error here. This should have been a negative 10, right? If we're multiplying all the terms, not just some of them, by 2, this should have been a negative 10. I'm hoping you already picked up on that, and you're probably wondering if I was and when I was going to pick up on that. All right, good. So we've got this. So our function is x squared minus 4x minus 5. We're going to put that into our y equals of the calculator. So let's go over here to the y equals. We're going to put in x squared minus 4x minus 5. All right, and that's our y1 is called f of x. Now you can retype everything, or you can simply do this. Check this out. We can go 2 times what's in y1. So check this out. We're going to do alpha, and then the trace button here. So eventually it's doing 2 times y1. And then in y3, we're going to do half times y1. All right, so I'll go make a little parenthesis, or maybe I'll just do a mini fraction here. All right, so we've got half of y1. Again, it's alpha, and then the trace button to get the y equal the y vars. All right, so we're going to see, I wonder if I could change the color here a little bit. Let's shoot up here and change the color of that second one. I don't want them both red. Let's see. Let's change the color to be black now. We already got a black one. Magenta. Great. So we've got red, magenta, and black, and the line is okay. All right, so see if we can make those adjustments. So I've got 3 different ones, red being the original, magenta being the 2 times, and black being the half times. So let's hit zoom 6 to be in a standard window. Okay, so we said red was going to be our original. Then we see, hopefully magenta is going to come up. And then that one looks like it is stretched out vertically. And the black one is compressed vertically. Now there were some instructions over here in terms of using the same window axes. So we're going to change our window to be from negative 20 to 20 in the y, negative 3 to 7 in the x. So let's shoot over here. I'm going to press window. And we're going to go x was -3 to 7, and our y's were -20 to 20. Now just hit graph and it will preserve those window scales that you've made. I've obviously screwed something up here. Maybe it only went 2 in the positive y. Alright, so now we've got our window range. We can just hit graph. It will proceed and make that graph. And the black one where it was half as big in the y direction. So let's come back and make some graphs. You can either make your sketch based on my sketch, or you can base it on the calculator screen. You can rewind a little bit and make some sketches. Try to get the significant points of the graph correct in terms of approximately where the vertices are, x-intercepts, etc. As you're sketching out those graphs, let's skip part C for a second. See if you can think about the answer to D. What points did not change or did not vary? Why did that happen? Play the recording when you're ready. Okay, so hopefully you made your sketches. You thought about this question. Obviously the x-intercepts are the same, right? And you think about it, all those x-intercepts have y values of 0. All right, so the way I said it is the x-intercepts have y values of 0 which are not affected by the multiplication by the scale factor. So if you double a 0, it's not going to change anything. So that's why those points don't change. All right, and let's finish up by looking at the minimum feature on the calculator, which is another way. All these graphs have minima. It's another way to get the vertex, right? Without having to go through the axis of symmetry and then subbing in the x value to get the y value, etc. So check this out. Or run your calculator if you have one. If not, you can just play along. You're going to hit second calc, and you've got some choices there. We want minimum, choice 3. And up at the top, it's identifying which of the 3 parabolas we want to find the minimum of. And you can control by up arrow which one we're on. And it's asking me questions. It's going to ask me 3 questions. What's the left bound? I just need to be a little bit to the left of the where I identify visually. There's the lowest point. And I hit enter. And then just move a little bit to the right of that point. Notice how it's got these vertical like boundaries. Okay, it's got to be somewhere in the middle there. And then you just guess. You can just be anywhere close and just hit enter. And so it's saying the minimum is at 2. Let's just basically say that's 2, comma, -9. All right, so we'll just keep that in our head, 2, -9. And then our other function, I want to repeat that process. So I'm going to go second calc, and I'm going to do choice 3 again. I want to repeat the process for the second function. All right, and then again, left bound, right bound, enter. And again, it's 2, -18. And the final one. Okay, and you can work that one out and play the recording when you're ready. All right, so this is our vertex for the graph that was compressed. Interesting that it's not exactly 2. Sometimes it's a little more, sometimes a little less, but let's just consider that a rounding error within the calculator's algorithm for finding the minimum. All right, so jotting back over here what the minimum values are, we had those 3 points. The original one was at 2, -9. Okay, that would be like right there-ish. Then we had G, which was our stretched out graph, 2, -18. Now no surprise, right? It doubled the value of y, kept the x the same. And finally our H was at 2, 4.5, or -4.5, which is half of -9. Thanks for watching.